Professor Bialis here. In this video we're going to be talking about section 9.1, which is covering compound inequalities. Now before we get into the inequality application of this, I want to talk about two basic terms that we're going to be utilizing within the compound inequality discussion. Okay, so let's look at this as just a general idea, and then we'll start applying it to actual inequalities. Okay, so the two words that we're going to be working with a lot are conjunction and disjunction. Okay, now a conjunction can be thought of and expressed in many different ways. We could think of it as an and statement. We could think of it or call it an intersection. We could symbolize it using this, okay? Or, and I like to think of that like a, so to speak. And then you could also just generally think of this as overlap. Now let me explain that a little bit. When I deal with a conjunction, I would be thinking of and statements. So like this tie is black and white, okay? Intersection. Now when would that come into play? Let's say a friend calls you and says, hey, come pick me up, I'm on Jefferson and Hobart, okay? You know exactly where that is. Jefferson and Hobart is where the two streets intersect. That's the intersection of those two streets, okay? So that's where these two words kind of come together. A lot of times in math, when we're making a statement, we want to keep it as concise as possible. That's where this symbol comes into play. So instead of writing the word and, a lot of times we'll use this. And then the overlap, that's just another way of thinking about these statements. When I talk about, again, Jefferson and Hobart, that's where those two streets overlap. Okay, so this is just different ways of expressing the same idea. Now, when we deal with a disjunction, what we're going to be looking at there are or statements, okay? So I would say that this tie is black or orange, for instance. Okay, I'm not lying to you by saying that. It's definitely not orange, but if it's black or orange, well, it's black, okay? There's some black in it. So these are or statements. Now, the intersection is going to be changed out for what we call a union, okay? Now let's think about that Jefferson and Hobart example. Let's say a friend calls you and says, hey, my car broke down. Come pick me up. I'm on Jefferson or Hobart, okay? What does that mean? Okay, you're on Jefferson or Hobart, you're going to be searching for a while. So we call that a union because you're just unifying all of those parts of that statement. It's not just where they overlap. It's anything and everything that was involved gets lumped into that statement. Okay. Next, if you were talking about a symbol for that, we would just invert this, and the reason for that is because it's a U for a union. Okay. And then last thing, we're not looking for overlap, okay? Again, that Jefferson or Hobart, we're looking for any and every spot along those streets. So here, we just use anything and everything. Okay? Now, again, we will get to the inequality aspect of these in a second, but let's just keep this kind of general, just to, again, illustrate what these are talking about. So let's say I give you two sets. And let's say set A is 3, 5, 7, 8, and 9. And set B is 2, 8, and 9. Okay? Now, let's say I ask you, given those two sets, and don't worry about where these are coming from, they're just given to you. Let's say I ask you to find A intersected with B, okay? A intersection B. We're looking for this conjunction. So we're really looking for what elements, what numbers, are in A and B, okay? And in that case, what do we have? We have that 8, whoops, forgot that brace here, and 9. That's it. Those are the numbers that are found both in A and B. Now if I switch that and I look for a union B, I'm looking for anything and everything that's in A or B. So now I'm going to use 2, 3, 5, 7, 8, 9. I unify both of those sets and I just list everything that I see. Okay? So again, I just wanted to illustrate one more time the difference between this type of a statement and this type of a statement. Okay? And versus or. Now let's go into the inequality aspect of this. Now, this is a compound inequality simply because we're taking two separate inequalities, compounding them into one statement. Now, this statement is a conjunction, okay, or we can call it an intersection type of statement. Now, regardless of what this word is, the first thing we need to do is solve these. And when we solve them separately and the same way we always have. So all I'm going to do is subtract a 5. X is less than 4. And then here I'm going to add a 1. And then divide by 3. We have that. We didn't do anything new. We didn't do anything different. We just solved two problems in one. It's at this point that we need to try to pull this all together. Okay? So what I'm going to do is I'm going to graph both of these inequalities on a single number line and then interpret my findings. So I'm going to draw a number line. I have a 4 and a 1. So I'm going to put those two values on there. Make sure they're in numerical order. And then I want to go less than 4. So I had an open dot and I went this way from 4. Okay? I'm doing the up and over just so I don't make a mess on my number line. The 1, I want to go less than 1. So I have an open dot and I'm going less than 1. Now this is where I have to interpret that graph. This is the moment where I pay attention to this. Up until this point, I didn't really care that it was an and. But now I'm looking for the intersection or the overlap. So where does those two inequalities or that shading overlap? That shading overlaps just in this region here. So what I have is a negative infinity to 1. Always parenthesis here. This was an open dot, so I have a parenthesis there. And that is my solution to the inequality. Okay, so again, the fact that it had that and there really didn't mean anything to us until the very end when we read that graph. Up until that point, you solve them separately, graph them together, and then you read into it. Okay, let's look at another one. Okay, so on this one, again, it's an or statement, so it's a disjunction, or we could call it a union at the end. Okay, but right now we don't care about that. We have two inequalities, solve them separately. So I'm going to add a 2. And then divide by 3. And then here I'm going to add a 6. And I get a 2. Okay? I'm then going to graph them. Same number line. I have a 2, I have a 4. The 4 is going to have a closed dot, and then I go bigger than 4, so that goes this way. The 2 has a closed dot, but I want to go less than 2, So it goes that way. Okay? And now I need to interpret. Now remember, it's an or statement, so I'm not looking for overlap. I'm looking for anything and everything. Where is there shading? Where? Anywhere is there shading. That shading occurs here and here. Okay, so I'm going to use it all. I have shading from negative infinity to 2, and then I jump and I have shading again 4 to infinity. Parenthesis, bracket, bracket, parenthesis. Always parentheses on infinity, brackets on the 2 and the 4 because of that closed dot. And then I'm going to combine these with that U symbol to show that that's one solid statement. Okay? So again, I didn't care that it was an or until the very end when I read the graph. Now, just for the sake of discussion, let's look at how this would change if this was an and. Okay? Nothing about that problem would change except for the answer that I interpreted at the end. Everything else would be exactly the same, except now I would be looking for where that graph overlapped. Well, in this case, it didn't overlap at all. So what I would say is no solution. Okay? Because there is nothing that will work for this and that. There's nothing that is bigger than or equal to 4 and less than or equal to 2. Okay? So, let's look at a few more. Okay. So, again, start off by solving each of these individually. So I'm going to add a 7. And then here I'm going to add a 6. And then divide by 2. Okay? Then I graph them. Six is going to have a closed dot, and I want to go less than 6. 4 has a closed dot, and I want to go bigger than 4. Now, this is where I say, okay, it was an or statement. So what am I looking for? Or means I'm using anything and everything. So where is their shading? That shading goes in both directions infinitely. So everything is shaded. So what I have is negative infinity to positive infinity. And there we go. Okay? How about this? Now, this is different than what we've seen so far. We've always seen two inequalities that have an and or an or in between. Here, we have some weird looking three-sided inequality. Okay? Whenever it is written this way, there's a couple things I want you to remember. First of all, it's always understood to be a conjunction, an and statement. The two inequalities that are being connected are this one and this one. Okay? Now, the other thing that I want you to remember with this is what you do to one side, you do to all three. Okay? So if I were to solve this, I'm going to solve this the same way I would solve this. Okay? So if it helps, cover one of these up for a second. Don't erase it, just cover it up. How would I solve this? I would probably subtract a 1, but make sure you do it to all three. So I get negative 4 less than or equal to x over 2 less than or equal to 4. Okay? Then I'm going to solve that. I would multiply everything by 2. But don't forget all three sides. And I get negative 8 less than or equal to x less than or equal to 8. Okay? Now, when you are graphing this, okay, honestly, the graph can be bypassed. Okay? Just make sure that you have a smaller number here than you have here, because you should go smaller and then bigger, bigger, bigger to that bigger number on this side. Now, if you wanted to graph it, I'm just going to show you this in this one example. Let me show you how that's done. You have negative 8, you have 8. If I were to graph this, I would have a closed dot here, and I go less than 8. If I graph this, I have a closed dot here, but I want to go bigger than negative 8. So I'd go that way. Okay? Now we just saw an example like this. However, in that previous example, we said it was negative infinity to positive infinity. In this case, it's different because remember, this is understood to be and. Where is the shading overlapping? And that's in between those two values. And we go negative 8 to 8. Like so. Okay? So, one thing that I would say about that is whenever this is written in a three-sided format and you have a small number on the left, bigger number on the right, it is safe to say you are always going to be shading in between. That variable is what the shading is representing. That's in between, the shading's in between, you just jump to that. However, if you are still a little shaky and hesitant on that, you can go through that graph. But in these three-sided, again, I would probably just bypass that graph. There's not really anything to interpret when it's written as a three-sided like this. When you have that and or word in between, you need to graph it to interpret what's really in front of you. Okay, but these you can kind of bypass that. Let's look at one more example. Now in this case, we're back to that three-sided inequality. Okay, we know it's a conjunction. Let's solve this. I'm going to cover this up for a second. How would I solve that? I would probably subtract a 1 to get 4 less than negative x less than 8. Okay, again, I'm covering this up just to kind of visualize what's going on. How would I solve this? I would divide by a negative 1. Now remember, there's something with that. I get a negative 4, I get an x, I get a negative 8. If I just leave it as is, and I do this, does that make any sense? That you go from negative 4 and you get bigger, bigger, bigger to a negative 8? That's the opposite. When we divided by a negative, that same rule applies here. When you divide or multiply both sides by a negative, you need to switch the symbols. Okay, and here, if you're paying attention, you'll see right away something's wrong. Now this makes sense, because I'm going from negative 4 smaller, smaller to negative 8. That makes sense. However, I don't want to leave it like this, because I always want to write things in numerical order, small to large. So I would flip this entire thing and go from negative 8, bigger to x, bigger to negative 4. Okay, so whenever you have that flip, okay, make sure you flip it because you divided by a negative, but then flip everything so you have that true correlation from the small to the big. Okay, so what I get here then is something that goes from negative 8 to negative 4, parentheses because there's no or equal to. Again, in this case, it is safe to say, as long as you're going small to big, that the shading is going to be in between. And here's your interval notation answer. Whenever we have inequalities, we always want to write those answers in interval notation. That's just kind of the standard way of writing those. Okay? So, that is pretty much it for section 9.1. As always, work hard. Let me know if you have any questions, and I'll see you next time.